can do the talk without the alarm going off. Very nicely on the cappelli to talk about Coulomb blockade. Thank you.
Thank you. Thank you very much for inviting me in this nice place. Just arrived. I like it. And okay, this is talk somebody maybe already saw in Amsterdam conference, but nevertheless. And this is about this proposal of Coulomb blockade as a probe of the features of quantum Hall states, and particularly non-abelian Hall states, and it seems that it could be seen in the near future. So it's also phenomenological interest. But okay, what I will discuss is how to get this Coulomb blockade from a partition function, and which is very convenient, and then what are the features of this conductant peaks, and what are non-abelian and abelian features. So a couple of transparency first to recall what is conformal-field theory description of quantum Hall effect. Maybe you know this already. So in fact there are two, because you have this droplet of electrons in the whole state, and there are bulk and edge excitations, and they correspond to each other. And so there is in fact two ways to connect to conformal field theories. If you have a conformal field theory correlator of two fields, then it is both describing the wave functions in the interior, where zeta is a coordinate in the plane at fixed time, and also describe correlator of with correlator of edge excitation on the space-time cylinder, which is the boundary times time. So this other variable zeta. Very often is the same function that you connect through this common boundary circle, and so they are the same function by analytic continuation very often. And this correspondence between bulk and edge is common in Chern-Simons theory, which correspond to conformal field theory description, Chern-Simons topological theory. And for example, if you take simplest conformal field theory, which is so-called Luttinger liquid, you show that there are fractional charge and statistics of excitation by this exponent takes rational value, fractional value, and so you get fractional charge and fractional statistics. And so what is important, the two aspects are important, because from wave functions you get the braiding of anyons, and with all the implications. And instead from edge correlation you can predict something about experiment of conductant experiments in which you inject some small current, and then you observe scattering of edge states and so on. So let me also recall something about non-abelian fractional statistics, and this is features that is very important now for the attempts to define to use this system as for quantum compensations. And the idea is very simple, is that in fact you can have correlators of conformal field theory which are made of several pieces. And for example, the best known example could be realized in this 5-valve state. And the conformal field theory corresponding is a Luttinger liquid or boson, free boson, and then the conformal field theory of the Ising model, which is made of 3 fields. Probably you all know this, but just let's go through rapidly. Okay, and the point is that in these Ising fields there are fusion rules that involve more than one term on the right, and so you have 2 channels in which these two fields can fuse. So if you have a 4-point function, you can fuse the first 2, and then you have 2 possible intermediate channels corresponding to 2 pieces, 2 independent pieces of this function. So in fact this is an analytic function. Is the simplest case is hypergeometric, and so when you do an analytic continuation in the z variable around points to make like this, you make a braiding of anyons sitting at points 0, zeta, 1 and infinity, then you have a 2x2 transformation. And so this 2x2 transformation is a unitary matrix, and you can diagonalize one, but the other one is non-diagonal. And so you get an element of the unitary group of U2, 2-dimensional matrices, and so you have a non-abelian statistics. Okay? That's the way you can. And so this is all facts of conformal field theory, which are more than 30 years old, but recently they have been brought, analyzing a lot and reanalyzed and expanded to figure out the possible braidings you can have, possible matrices you can realize with it. So what is the talk I'm going to tell is not about this braiding, so this interference, but is rather this other situation in which you form an isolated droplet. So you can do this so-called annual interferometer, and you can have 2 regimes in which you have a weakly interacting at this point, or very strong pinching. Okay, strong interacting. And so here is the weak interacting limit is convenient to let one edge states to go around or go directly, and then make interference pattern which reveals the fractional statistics or non-abelian fractional statistics from the interference between these 2 types of paths. And instead what I'm going to talk is this other regime in which you have an isolated droplet, and then at this point only the electron can tunnel here because the fluid is discontinuous, okay? And so you have this Coulomb blockade conductor peaks. This means that once there is an available energy state inside here, electron can go in, and so you have a peak in the current. And what we are going to see is that Coulomb blockade is these peaks have some patterns that can test the property of the conformal field theory, which describes the droplet, the whole droplet. Okay. So what is Coulomb blockade? Well, it's very simple. When you have a small droplet, the electron, and you put some bias, then the electron cannot go inside immediately because there is a charging energy. And this has to be sufficiently small to see this effect, okay? And so when these 2 terms compensate exactly, then you have 1 electron enters, and this is because the charge is quantized, then it makes peaks, okay? And in fact, this happens when these two terms are equal, and so the energy level are degenerate. So when inside the system there is an empty level which becomes degenerate with the field level. At this point, electron can go through. Okay? So it's a way to do spectroscopy of edge states. For example, in the simplest one-third state, you know that there are 3 sectors of the theory corresponding to 3 values of the fractional charge. So when you add an electron, you stay in the same sector because you vary the charge by an integer value, okay? You got 1 to 1/3, okay? And how you can realize these peaks? Well, you can do by deforming the area of the droplet. If you deform the area of the droplet, then the energy levels, which are discrete and given by conformal field theory, which have the typical edge spectrum, which is of order 1/r, the size of the sample. They are discrete levels. When you deform the area, then they acquire a capacity energy, which is proportional to the charge at the boundary. Okay, so this is the charge as square. So this energy at the edge is, roughly speaking, 1/r, the charge square. And then you have the Fermi velocity. So if you deform the droplet, then you have a background charge that adds to the charge of the excitation, and then you have this behavior. So if you make a deformation, these discrete levels becomes parabola, like here, that are plotted versus the area deformation. And so, suppose you have, let's say, E0, which is the ground state, which is full, and E1 is an empty electron level, okay? Then you deform, you go from here, you start to deform the droplet, this energy, this level energy goes up, the ground state at a certain point it crosses the first excited level, which is E1, and at this point the electron can enter and you have a peak, okay? And so, it's very easy to find out what will be the spectrum of the peaks. The peaks are equidistant in this area change. In fact, the area here, these are numbers, so they have to be dimensionless, and the way to make a dimensional number is by combining to the quantum of flux, okay? And so this variation is the inverse filling. And in terms, so if you go back in terms of sigma, this is this quantity, which is very simple to understand because this is precisely the area, and 0 is the average density of the fluid. Okay? So if you deform the droplet of this amount, you create exactly the space to put another electron at the same density. Okay, so this is a simple classical idea of how the electron can enter. Okay, because you made space for at the fixed density, which is nu, which is related to nu, to filling fraction. Okay, so this is very easy to understand. This is just a classical. Okay, so the problem is to obtain these peaks for more complicated theories, which are relevant, which are the hierarchical Jane states with these filling fractions, and Pfaffian and Riederer states. They involve the following conformal field theories. E1 stands for the abelian Luttinger liquid, is always present, and there are also neutral sectors. So excitation, physical excitation is made of charge and neutral part. We saw before in the Pfaffian case, the neutral part was the Ising fields. Okay, is the simplest case here, k equal to 2. Okay, and the neutral and charge sector are combined in a trivial way. So these affect the result for the Coulomb peaks. Okay, Okay, and then there are selection rules for the process of the electron entering the droplet. It depends on the state of the droplet, whether inside the droplet there are bulk quasi-particle or not. And so there is the issue of finding the right sector, the right fusion of the electron with the existing excitation inside the droplet. Okay? So it's not completely obvious what you get as a result, and because of this involvement of the fusion rules, you have this peak test the qualitative features of conformal-fitted. So they test the conformal-fitted description. So what is my main point is that if you use the partition function, you will find out these Coulomb peaks in a very easy way. And the partition function is a known business of conformal field theory, and the main point is that the partition function should be modular invariant, and there is a relation between modular invariance and the fusion rules that was found by De Linde and by other people. And so partition function is a list of all the possible states, and it contains these different sectors which are related by fusion, and most of them are already known. So first we start with a more complicated geometry, which is the annulus, and then we go to the disk. The reason is that the annulus has two edges, and one is chiral and the other one is antichiral. Okay? And so it's better to obtain the partition function, and then we shall get the one of the disk very easily. Okay? So what is the partition function? Well, it's a grand canonical sum in which you have energy and charge. And in fact, these two parameters are complex. So you have charge is coupled to the electric potential, then you have a chemical potential, and this is the energy which is proportional to 1 over r, as I said, times the conformal dimension. So this is the trace over possible states, okay? But in fact, the trace decomposes itself into sectors, the sectors of the theory. For example, the sector with the fractional charge 1/3 is a sector, 2/3 is another sector, and fractional charge 0 is a third sector. Okay. So these sectors are orthogonal. So the sum, the partition function then decomposes into sum of independent pieces, each one for a sector. Okay, what I call H lambda. Okay, lambda stands for the fractional part of the charge. And so if you have, for example, 1 over p fraction, then you have a p-value of the fractional charge, you have the sum of p terms. And the fractional charge on one side should combine with fractional charge on the other side to get the integer charge, total integer charge, okay? And so this is so-called partition function of a rational conformal field theories. Rational conformal field theory stands for the fact that the quantum numbers of charge and dimension are rational. And the sum here extends over a finite number of terms, which are these, for example, fractional values of the charge. Questions? Yes, questions so far? Please.
I was just wondering why the partition sum only goes to p.
Yes? Because, well, P is the number of sectors. Then inside each sector the sum goes to infinity, because this is a infinite sum, okay? Yes?
Let me maybe explain the
Yes.
question. We were looking at these sums on the torus, and then on the torus it wouldn't go to P but to 4P, because you have the possibilities of choosing boundary conditions on the torus if you go around. And I would have naively guessed that you would also have the freedom to choose the boundary condition when you go through the whole, but that doesn't seem to be the case.
Yeah, yeah. The different boundary conditions are different values of P. Here. For example, if you take a fermion, you will have 4 terms here. For form of criteria 1 fermion, you will get 4 terms, because it's plus minus on the 2 sides of the torus. That would be the partition function of 3 fermions on the torus. We have 4 terms. But this is a C hot 1, it's a boson, so there are as many terms as there are the fractional values. And there is a technical point here, however, that this maybe the answer is this, that this is only invariant over this t-square modular transformation, not t. Because
Sorry about that.
it's fine. Okay, so how do you get this? Well, there is a procedure which is mostly algebraic, in which a part of the sum, these sums here over the sectors, are given by characters of representation of the Virasoro algebra or the conformative theory. And then to combine this, you use these conditions of modular invariance. They are geometrical conditions on the different ways to write the geometry, but they also have a physical meaning. Here is listed. For example, this tau is a ratio of the 2 periods. So there is one period which is the circle for edge, and the other period is the temperature. Okay, so you have a torus, and this is just a redefinition of the torus, and also this is a definition of the coordinates of the torus. So it should be invariant. This is geometrical fact. Okay. But these two conditions, they also have a physical meaning, and here is that the condition is that the excitation should have a half-integer spin. So the difference between this 2 and 0, which spin, has to be half-integer. Normally in conformative theory has to be integer. Here is half-integer. Then this S transformation is a condition of completeness. Physical meaning is that of completeness. Is the fact that you exchange space and time, and so you require that the set of states that exist at a given time are also the same that allows you to propagate any state in time. Okay, so it's condition of completeness of the basis. So I think because of this S matrix then enters into the within the formula for your fusion rules, this is also completeness of the fusion rules. So the fact that you have a closed set of fields under the fusion. Okay. Then there are two more conditions regarding this zeta variable, which is related to the charge, and this is in geometrical terms. This is a coordinate on the torus, so it has to be periodic with the 2 periods. And physically, the condition is that zeta plus 1 brings up here a factor of e to the I pi q, and so in order to be invariant, you should have the q minus q bar is an integer. That means that excitation globally should be on the two edges should have integer charge. And this other thing is in fact a way to create a flux inside the annulus, and so you create a quasi-particle and you change sectors, because you create a one-third quasi-particle, then each sector goes change charge of plus one-third. It's so-called a spectral flow. We'll see more of this later. Okay. So once we have this annulus partition function, then you can read the different sectors that I call theta lambda. They are only one chiral part. They describe the disk. And in fact, there are several of these for each value of lambda, okay? So 3 in this case. Because the type of states on the boundary may depend on the fact that inside you have a fractional charge, okay? So the total charge has to be integer. So if inside you have a quasi-particle of charge one-third, you have to use theta 1, which corresponds to charge one-third plus integer. Okay? Okay, and this is the expression, is a theta function, and you see that is a sum overall. This n is the number of electrons, and here you see this factor is the charge of the electron, and this factor is the energy of the electron. The same formula we saw before. Okay, it's quadratic, and then I put this deformation sigma for area deformations. Okay, so it's just the sum of all the possible states with fractional charge lambda over p. Okay. Okay. So. And so another important fact is that P, which is a dimension of this set of partition function, which is also dimension of the S matrix, is topological order. In this case, is P. Okay. So once I have this partition function for this sector, it's very easy to find the Coulomb blockade conductance peaks, because in this sum I have certain ground state with some fractional charge and all the electron excitation. And so I just compare values of energies here corresponding to varying the charge of 1. Okay? So I compare two energies with different values of n by 1. Okay? So so I get the same result as before, that there are equidistant peaks. This is a Laffin case. Okay? And okay, and also I see that because the formula is linear in lambda, if I change the sector, if I change the value of lambda, the distance between the peaks is the same, because just a shift of the coordinate. So the distance between the peaks is the same. So, okay. Now we go to something more complicated, in which this machinery of the partition function is really useful. These are the multi-component fluid or hierarchical states, and the standard theory involves m Lattinger liquids with a specific configuration that has a SUM symmetry. So there are m boson with SUM symmetry. the charge and the SUM weights are not orthogonal. That means that excitation are combined with charge and certain SUM weights combined together in a non-trivial way. Okay, so what I said, excitation has a charge part and neutral part that are tangled together. Okay, and the topological order is the denominator here, and so there are this number of sectors and the corresponding number of these partition functions. And these were already found, and I have the following form. So this A runs over the sectors, and each one is itself a sum of terms. There is a charge part, as before, which is this theta function I call kappa. And then there is a neutral part, which I call chi beta. It's neutral, so I don't put zeta, put z equal to 0. Okay? And these are the characters corresponding to the SUM level 1 algebra. They are also known functions. And so this is a known formula. It's not so important the exact form of the function, but their periodicity properties, their basic properties, and how they combine together to get these correct numbers of sectors, and how they combine to make a modular transformation that they make transform among themselves into by linear transformation, which has dimension the topological order. So this theta A combine among themselves, and this is dimension, Q is the dimension of the S matrix. Okay? And so how it goes. So for example, let's take a simple example. When you take M equal to 2 and Q equal to 5, to fifth state, then we know that this character, there are 2 of them, Chi1 and Chi2, and there are 10 of them. Their form is deduced from the spectrum of charges, of dimensions, and so on. You combine together to get a modular invariant combination. You come up with this formula. So what it is? You have to combine them in this form. So you get, for example, that you get five values, because the denominator is 5. And for example, the ground state is theta 0, which has a 0 fractional charge. And then you look inside this formula, you see that these are some charges with integer number of electrons, and this is odd number of electrons. Okay? So when you want to see where it goes, the electron, one electron that you add to the droplet, then you have this conductant peak, you have to compare the ground state, which is here, with the first excited state, which is here. So at this point, the energy has a quadratic parabola from this charged mode, but also a constant contribution from the neutral part here. So this Chi1 has energy which makes a shift upward of the parabola. And so at this point, the peak occurs when the crossing of the parabola, they are shifted a bit ahead, and so the distance between the peaks is different. Okay, so you have 2 peaks which are closer than the other, due to the presence of this neutral component, which is a contribution to the energy. Okay.
Is there an assumption built in that I missed, that all edge velocities are the same?
Yes.
Yes. Certainly, I think it's known that that's not true generally.
Well, yes. I can. What I assume here is that the charge velocity and the neutral velocity are different. That's I can do.
Oh, you're going to assume the charge and neutral
are different. But if you can also suppose that the neutral one, because they are n minus 1, they could be also different among themselves. That I don't. But let's see. Okay. So the distance, in fact, there is extra distance. This is case 3. Before it was case 2. Okay. The extra distance is in fact the ratio of the velocity of neutral to charge, which is supposed to be small, maybe 10%. Somebody says that it's 0, but then in this case you don't see anything. You don't see any modulation of the peaks. But there are also experiments that would favor a small velocity, but not 0. Okay, so this is open. Of course, if the neutral, because this modulation of the peaks is all coming from these neutral sectors, if they don't have, if they don't move, they don't see any. You don't see any modulation. Okay. Okay, so you have this. So because of the contribution of the neutral energy, you have this modulation in the distance of the peak, and then there is another fact that these characters have a multiplicity. So in fact, when there is an electron that there is a one available state which the electron can go, in fact there are more than one that are simultaneously available by this number. Okay. So m is fixed by is a numerator of the filling fraction, and beta is the sector is the number of, roughly speaking, the number of electrons you add to the droplet. So if you start from the ground state, which is unique, then the first jump you have 3 at 3 and then a binomial, okay, and so like this. And this I put a little bit separated because okay, there can be some final size effect that destroy the SUM symmetry. That's a possibility. Okay, so this is m equal to 4 and so on. So this pattern is rather nice, and if you can see it, then would be a test of the edge theory. Because the fact that there are m components for nu equal to m divided by the denominator has been disputed, and so it's not yet clear. Okay. In fact, there are also other theories which don't have so many components. It's you know, when you have these fractions accumulate to 1/2 from one side and the other. So when you reach 1/2, then the number of components of the edge grows, and eventually it can be very big. So people don't believe that you can have a multi-component edge with 10 edges or even more, because when you approach 1/2, maybe. Okay, you see this formula. Okay, if you take p equal to 2 and you change m, you approach 1/2 from the two sides, and so this 1/2 is not a compressible fluid. Okay, and so the number of edges grows. Okay, so there are examples of theories that don't have this multiplicity, and this diffracting is what I proposed some years ago. And okay, maybe I should go to the next. So what is interesting now is to see what happens in the non-abelian case. Well, you can repeat more or less the story. The new thing is that the neutral part involves the parafermions. And so parafermions are not completely trivial conformal field theory. You have to get used a bit to them. They are not so complicated. At least at the level I use their properties. You have to know how many they are, what are their dimensions, or what are their spectrum. It's very simple, okay? at least in this coset. It's a coset, so parafermions are characterized by the numbers of the coset. SU2 has a SU2 spin, which is L, and has a maximal angular moment, maximal spin, which is the level of SU2. And then the coset is with respect to the spin projection, so the third component, which is an abelian number, is an abelian charge mod 2k. So the parafermions have these two quantum numbers, total spin and spin projection, and they have the following periodicities. So this is the main domain in which you see this is L, and then M can go from plus L to minus L, like ordinary spin. But then there is this sector is reflected on this other triangle to make a structure which is periodic of 2k in this direction. So in this case 3 is 6 periodic, okay? It is like this, okay, from the coset. So in fact these sectors, these fields, parafermionic fields obey this rule. And also in these theories, the neutral part and the charge part are combined by a selection rule, which is called, can be called parity rule, which is that the value of the fractional charge is equal to the value of the spin part of the parafermion modulo k. And also topological order is obtained in this way, because this is the number of sectors of for the fractional charge, this is the number of parafermions, but they combine in this, which kills k component, and so you get the topological order. Okay? And the partition sums are of the same type. They are a sum over combined neutral charge and neutral parts in this way, because you see this way respect this condition that fractional charge is equal to value of m mod k is the same, k goes away. So these sectors are characterized by the same indices of the parafermion, the total spin and this spin projection that now is tied to the fractional charge. Okay? And so now you know from this formula, you know that adding electron is just comparing one term here with the next term, and so you have to compare the corresponding energies. And okay, and then you have a pattern of peaks, which is the following. It depends on this quantum number L, which is roughly speaking the number of quasi-holes, because the elementary quasi-hole is a sigma 1, is the spin field, and has L1, so there's a spin 1/2 in fact, no? And so because this is spin times multiplied by 2, so there's to be integer, okay? So this is spin 1/2. So L is the number of quasi-particles in the bulk, and the pattern depends on the pattern of peaks depends on how many quasi-particles we have in the bulk. So if you have 0 of or k, then the distance between the peaks is the following. So it means that as before there are groups of k together separated by distance, and then you have another group of k. If instead you have a number of quasi-particles, then the groups are L and k minus L. In particular, if you have k equal to 2, which is the Pfaffian, if you have 0 or an even number of quasi-particles, then you see this pairing of peaks. If you have an odd number of quasi-particles, then here you have groups of 1, so that means that the peaks are equidistant. Okay, so this was somehow called the even odd effect, that could be a signature of non-abelian statistics. Okay? So then there is you can also repeat the analysis. This was already done by Stern, collaborator, and Scoutens and other people. They said that in fact there could be a mechanism in which the sectors in which electron goes changes. How is possible? Well, because it could be possible that the neutral part of excitation at the edge and in the bulk fuse together and to create another excitation which has a lower energy. Okay, whether this is possible or not is not clear at present. People say that maybe it is possible, but it takes some time. Somehow this excitation in the this excitation inside the droplet should interact with the edge and decay. So maybe it takes some time. Okay. Anyhow, if there is such relaxation between bulk and edge, then the neutral part can change. And then you have to see what is the possibility for the Coulomb peaks. It's very simple if you plot these are dimensions of a parafermion field. Okay, so you have to when you add an electron, somehow you move vertically up here. And so you go to a state which is high energy in this surface. And decay is possible by this transition that does not change the value m, so it does not change the charge, because charge at the edge cannot change, but neutral part can change. So because this is related to charge, cannot change. So this has to change a minimum of 2. So it can jump down here, this is the red thing, and then this is a relaxation. At this point, the next electron goes up in this direction again, and then you come here, and then you fall down again, and this is another relaxation. So you figure out what are the possible peaks, and you find that if you have this relaxation, the structure of the peaks does not depend on L, does not depend on the presence of bulk quasi-particle. It only depends on the value of K, which is related to the value of the filling fraction in this way. So that's more or less. Yes, a few minutes. So it's okay. So this is. So there is a modulation in the distance between the peaks, and it depends on the bulk quasi-particle, it depends on the type of conformal field theory. It tests some properties of the conformal field theory, which are a number of excitation, the sectors, the fusion rules. Okay. So another possibility is to vary both the area and the magnetic field. So you have to understand with these partition functions, which are fixed, which have indices corresponding to the quasi-particle, where do they go when I add some magnetic field? Well, it's very simple, because magnetic field coupled to the charge part, and it changes the charge of this part of the excitation. And for example, if you add one quantum of flux, then you know that these correspond to adding a charge equal to the filling fraction. And so this charge should change by an amount. This is the index. This index is a charge, is related to charge, should change by an amount equal to the filling fraction. And this is how it changes. But because this has a periodicity, this object has a periodicity, it goes back to use this periodicity, you obtain back the same sector. So you don't change the sector. When you add the magnetic field, you don't change the sector. So the overall effect is that the pattern that you had already here on the axis for variation of S, for example, here you see they have, for example, three close peaks separated by a larger distance. It remains the same. It's only shifted, rigidly shifted in V. Okay. In fact, it's a function of this combination. So this is how these peaks are seen when you plot both area and magnetic field. But it would be better if you could change the quasi-particle number. So if you, for example, could change L into L plus 1, then the pattern would change. And so here this distance would move. Okay. But in fact, it's not possible because you need to make this transition, which is not there, which is not caused by the magnetic field. Maybe if you do some other type of coupling, you can do it. For example, you can imagine to create, engineer an antidote inside the disc, inside the droplet, and then to charge it. So another type of coupling. Then you could get this transition. Okay, so this is a conclusion, and the idea is that this conductant peaks can test the edge states, and of course, because you have these sectors, there are some specific properties of the conformal field theory. It's a very clean signal because the isolated droplet is a very clean system. It does not have much environmental disturbance. So in principle, it's very clean. It's better than interference experiment in which you have it's an open system, so you have several disturbing things. However, the pattern of peaks is not particularly rich, so it's not great. I mean, it's clean but not great, I would say. And of course, the business of partition function is useful for many things, besides the study of Coulomb peaks. And so I think I'm going to use it for other investigations. For example, it has been already used, in fact, by Fendley, Ludwig, and some other people for studying topology and entanglement entropy. And also, it's a main thing for main quantity for model building. So I think it's useful. Thank you very much.
Questions?
So what's the experimental status of detecting these locate peaks and making?
Well, there is I mean, I don't know I tell you something, I did a search of maybe 3 months ago, right? So nowadays maybe it's important. But okay, this has been seen, that they claim that that they saw this. They claim. They did a small droplet, which is 1 order of magnitude smaller, 2 microns, and they saw this, and they say this is Coulomb peaks. Not with a distance, just stripes like this. And then if you can really see the stripes so clean that you can see the difference in the modulation and or even this substructure of the multiplicity that I don't know. I mean, I think it's reasonably doable in the future.
Questions? I've got another question.
Yes.
So you said that you can sort of move these parabolas up because of the additional factors. Could it happen that you move it so far up that it goes above the crossing line of the two parabolas nearby, so you actually lose peaks or they merge into one, or is this impossible because of the scaling? You would get a case where you would have to hop 2 electrons over 2 electrons. Or
It's possible, yes, but yeah, it
or
could
it
be
just doesn't
possible.
happen in these types of moments.
No, not yeah, it could be possible here, yes, but because it's small,
The shift is always small.
at least an order of magnitude. There is a factor of velocity which is probably 1 order of magnitude. Also, well, this is fixed, but this could change with the filling fraction. This changes with the filling fraction, because the denominator is the same denominator of the infraction. So, if you take a very large, in the series here, take a very large P, then it goes down. This parabola goes down, and so possibly you get what you said. But then you know that if you increase too much in the denominator,
sure.
also is not is unstable. So
can you see the sign of the neutral velocity here? For instance, the two fish.
No.
No.
So
So
this is not positive. No, because it has to do with energy, so you don't see the sign.
So there's no sign information.
No, I mean plus and minus is a sign, but it is understood through the value of the filling fraction, not through the sign of the velocity. It's, this energy always add because it's energy in both ways, in both cases. Okay, so this is a sign, but it's also different filling fraction. So.
Any further questions? If not, thanks, Andrea. Again. Thank you very much. So I would have to look up how they precisely do it.
Because if say that we are
For the theory,
Why do you expect that this?
you cannot think
but
of
people
it
don't
as
believe
a
in it. At a certain point, they have
Or
to.
you have to.
normally
No. All these movements are also going in the same direction. It's not like this is the normal J zero.
Rotating and spacing.
Not backing out thing of these U1
So-
Difference in spacing.
But is it
Yeah, for each one third is triple like that, but you could also write it.
Like this.
There's 2/5, 3 7 1, and you always have 3 modes.
Is it
One
for the-
is
is it
If you increase the number of elements,
for this particular game series. Yeah. They also do double layer case, and they need one charge and then 4
that this intensity
But it's exactly for this particular game series that they use.
What's your name again?
And
Oh,
yeah,
Targaryen, right?
slight details.
Yeah.
They put all the charts in one mode and then they need to fix the rest and that fixes it.
Yeah, that's a good point.
But I never really understood
Right.
what type of seed
And
it is.
I mean, but it is consistent
Consistent with compressibility or not?
Yeah, so they get teenagers as well, but it's also that they get different things. And so it could be that if you have a very shallow edge, that you get this when you try to bend, and if you have a really sharp edge, then everything will line up. No, I don't. But yeah, I don't. So it has. So you would have one over the denominator. Then charge mode can accommodate both the smaller squares and blocks, which is charge 1 over 7 or 1 over 9, and then you need that mode multiply occupied to make the charge 1 over there for the electron. Yeah, that's the minimal charge.
But it's true that they get this. They get the multiplier. In fact, they have a multiplier, which is M over 1. So each of these people is a connection.
So actually we keep it a little bit vague on purpose, so that hopefully context. But the idea is that you have a transition where the number of certain text anion becomes ill-defined, so usually you would expect that at the transition where the condensation happens, the gap would close, because the typical way that you expect condensation to happen is if the mass of the anion that condenses goes to 0. So and then if it goes through 0 in the vacuum of the new theory, you would have some undetermined number of superpositions.
But I mean, that's exactly what you want to do as well.
Well, yeah, sure, that's
well, so there isn't really a proper local symmetry in these models.
That I've never really fully understood what kind of theory.
But it's the reason we call it symmetry breaking is because, well, there's this analog of symmetry, which is the quantum or the modular tensor category.
That's a good point.
And the way it behaves in transition is very similar to what happens with symmetry breaking phase transition. So if you think, for example, the Higgs effect in the what happens is that some field, the Higgs field gets an excitation.
Okay, you don't like this M in
then
okay, I don't like it, but no. You have to go from
well, it's kind of complicated, but yeah. So the information theory certainly is broken. So